Hi, welcome back to AP Physics C, Unit 1, Electrostatics for E&M. So this is going to be where calculus does come into play a fair amount. And we're going to, in this video, we're going to look at what is known as Gauss's law. Okay, so Gauss's law is centered around flux. And the way we think about flux is that it's just the amount of something that passes through a given area. In this video, in this part, right, and you can see it's a big tool for electricity and magnetism. So in this area, in this particular unit, we're going to look at electric flux. And the flux symbol is phi or phi, depending on what side of the fence you sit on and how you pronounce this. So this is going to be the amount of electric field that's going to pass through an enclosed area. So mathematically, it's a dot product, okay? So the electric flux is equal to E dot A. Right, and so remember, dot products are a way to multiply the vectors, and we get a scalar number in return. And so another way that it breaks down is just to be simply E times A cosine theta. Okay, so what does that mean, really? It means that the electric field, to get the maximum flux, the electric field has to be parallel, right? Or the area has to be parallel to the electric field. Right, and so you can see here in this first picture, the flux would be E times A because the electric field is passing through that area, which the area is, if you want to say, open to the flux or the field for it to come through. As you move to the next video or next part of this picture, you got E dot A, and that's where the EA cosine theta part of the equation will come into play, right? Because the electric field is at an area or at an angle, we want this area. We want the one that puts the area parallel to the component, right, or parallel to the electric field. And then if we're perpendicular, right, there's no flux, right? So if you think about it, it's just like passing, it's the electric field that's just simply passing over the area that we're looking for. Now, Gauss's law will state that the sum of charged sources within a closed surface is equal to the total electric flux through that surface. So what does that mean? He's saying that the electric flux is equal to the amount of charge enclosed by that area over epsilon naught is going to equal this integral, okay, of E dot dA. Now, here in AP Physics C, right, it looks like a difficult integral, right? Calc 3, we call this a surface integral because we're looking at all these different surfaces. But the important thing is, for us here in this class, it's just going to be EA, right, cosine theta, right, depending on if you have, if you have angles involved. Okay, so what does that mean? You're going to have to remember some surface areas here because what we do is we surround the charge with a Gaussian surface, and then it's just such that the electric flux is perpendicular to each point of the surface, and the electric potential at every point is equal. So you're gonna have to remember some surface areas. The common one we do is the sphere, which the surface area is 4 pi r squared. You have a cylinder, I wrote an E, which is 2 pi r L or H plus 2 pi r squared, right? Because you have two areas, right? You have two end caps, which are circles, right? And then if I roll out that middle piece, it's just simply a rectangle where the circumference is one side and the length is the other side. And then the other one you would have to remember is a cube. But with a cube, some of the surfaces won't have the electric field passing through it, okay? So you just have to determine which, and in fact, all of them, which areas is the E field passing through, okay? So let's look at a couple of examples. So here we have a Gaussian surface, right? We have a cylinder. It lies in the uniform circular field with central axis, which is along the length of the cylinder, parallel to the field. And then what is the flux of the field through this cylinder? And so the way you think about it, you can see that in this diagram, there's three surfaces we're looking at, right? We have the two end caps, and then we have the one that would pass through the over the surface, right? And so imagine that surface is all the way, remember, it's perpendicular to it. And remember, the E field is also a three-dimensional idea. So if I do the flux for each, right, I'm going to call this over here 1, middle one 2, and then that one 3, right? So if I do the electric flux, E dot A, I'm just going to do EA, which in this case would be EA cosine theta. And so it'd be EA, excuse me, cosine of 180, which is negative EA. And this is like a deriving expression question. So the second flux would be EA, E dot A, right, or EA cosine theta, but it's perpendicular, it's the cosine, so that means it's the cosine of 90. So on the surface, right, the big main cylindrical part of it, we have no electric flux going through it, or no electric field passing through it. And then for the third one, which is the end, the right end cap here would be E dot A, which is EA cosine theta, which theta in this case is 0. And so that would be an electric flux of EA. Now I got to find the total. Well, I have negative EA from 1 plus 0 from 2, and then EA from 3. And so for in this situation, you would have, excuse me, you would have no electric flux, okay, because there's no part, there is part of the E field passing through it, but note that through one of the end caps, it'll cancel out. Okay, and the unit for electric flux is kind of a weird one. It's newtons times meters squared per coulomb. Okay, because the E, right, electric field is newtons per coulomb, area is meters squared. Okay, and so when you multiply them, you get that Newton times meter squared over coulombs. All right, and the next one, this is an old AP question, and what we have to do here is we have to define our surface. For one thing, note that at point P, excuse me, because that's what we're looking for, will be pointed up, right? And so basically what I'm going to do is I'm going to put a cylinder around this, okay? And the E field is kind of passing like this at that point, right? It's going up. So it is parallel, right, to our surface. And so we're going to use a Gaussian surface where it's going to be a cylinder of radius C, right, which you can see right there, and a length of L, and the charge enclosed would be this positive lambda. And we'll talk about what lambda is later. In fact, let's do it now. It's charge per length, and that's going to come into play in the end. So again, we're going to do our electric flux equation. So it's going to be E dot dA, the integral, but we know it's going to be Q over epsilon naught. Again, derive an expression, and as it works out, in all cases here in AP Physics C, that integral is just going to be EA, right? And so we're going to say equals Q enclosed over epsilon naught. Well, the A is going to be our cylindrical piece, which is going to be 2 pi RL, right? So it's the surface area, and it's going to be Q enclosed over epsilon naught. Now, Q enclosed comes back to this lambda, which is going to be Q equals lambda L. So I'm going to substitute that in. I'm going to use a different color so we can start distinguishing steps. So I'm going to say E times 2 pi RL equals lambda L over epsilon naught. L's cancel, okay? And so now I'm just going through and solving for solving for E, and then the last step we divide by that 2 pi R. And so it'd be lambda over 2 pi R epsilon naught. So that would be, now on the test, you need to make sure, like, what are they trying to ask you to solve it in terms of? Here they don't tell us, so we can leave it in this lambda over 2 pi R epsilon naught. We can also substitute back in what lambda is, which actually then brings L back in. So there's really two answers here. So if I substitute in Q over L for lambda, I end up with Q over 2 pi R L epsilon naught. So these two answers are the same, just one has the lambda in and the other one has just simply lambda. Okay, so that's going to be it for this video. In the next video, we're going to start looking at just electric fields based on different charge distribution configurations.